Now let us discuss chemical properties of group 16 elements. In this first, let us discuss their oxidation states. See, oxygen, sulfur, selenium and tellurium. They all shows -2, -2, -2 oxidation state because they try to accept 2 electrons to attain their own period's noble gas configuration. So they shows this. Yes, we have selenium in the selenites exist as selenites and tellurium existing as tellurites. But along with this, we cannot have any oxidation state of oxygen except in the compounds which it forms with fluorine, where like OF2 and O2F2, where it exists in the +2 state and +1 state, it all forms -2 compounds. Then sulfur, yes, it can show +6, +4 and +2. The reason being it can share all its 6 electrons due to the availability of the d orbitals, or it can share 4 or any all the 2 only. Selenium also shows +6, but it is more stable in +4 and +2, so that's not very stable. And tellurium again not existing in +6 or mainly existing in +4 and +2. So it's a very same thing. The stability of the higher +6 oxidation state decreases down the group due to inert pair effect, poor screening of the NS electrons, and the stability of the lower oxidation state increases. That's why we have tellurium existing in +4, also in +2 state. So these are their major oxidation states. Now let us discuss their compounds. Like, let us take first their hydrides. They all combine with hydrogen to form hydrides with general formula H2M. Like we can have H2O, H2S, H2Se, H2Te. I am not taking polonium because that is not mainly taken in this case. Now these hydrides, what is the first thing to notice? Their thermal stability decreases down the group. That's pretty obvious because MH bond strength decreases. So most stable is water and the least stable is this H2PO, the hydride of polonium. Then what we can say on this basis is their reducing property, tendency to give hydrogen, increases down the group because most easily we can break the polonium hydrogen bond or tellurium hydrogen bond. So that's the least basic reducing property the water is having, except this all can act as a reducing agent except this water. Then their basic nature, I am talking about Lewis base character, the tendency to give these 2 lone pairs that they are having, it decreases down the group. Why it decreases? Because charge density decreases with the increase in the size of the central atoms. So that's why the basic nature decreases. Then their structures. All of these are isostructural, sp3 hybridized, having bent structure. So it's very similar to like this one. And these are the 2 lone pairs these are having. Then if we compare their bond angles, what we find is bond angles decreases drastically down the group. It's because this, like in case of this water, we know it's 104.5 degrees Celsius and it's around near 94 degrees. The reason is because the size is decreased, angle is decreasing, because as the electronegativity of the central atom decreases, the bond pair repulsion decreases. So that's why they have come more closer to each other. Now let us talk about their boiling points. Water is an exception in this. We know that boiling point mainly depends on molecular mass, which increases down the group. So it should increase down the group. But what we have water as an exception, it's H2PO, H2Te, H2Se, H2S, and water being the exception because of the hydrogen bonding. It is an exception. So, and that is why what we find, all of these are gases and water is the only one which is present as a liquid. So, these are the hydrides of group 16. Group 16, and let's see their chemical properties in the form of their oxides. Now, group 16 element forms mainly two types of oxide with the formula MO2 and MOT. That means they form dioxide as well as trioxides. Now, we will be studying oxides of only the sulfur, selenium and tellurium. Sulfur forms, yes, SO2, sulfur dioxide, selenium also forms dioxide and tellurium also forms dioxide. They also forms trioxide with the formula sulfur trioxide, selenium trioxide, and of course tellurium trioxide will not be stable. The reason being it doesn't exist in the +6 oxidation state. Now let us talk about their nature. All of these oxides are, remember, acidic in nature. All of these are acidic in nature. When they dissolve in water, like if you put SO2 in water, it forms H2SO3 sulfurous acid, and when SO3 is added to water, it forms H2SO4 sulfuric acid. Now what is important to note about these oxides is, let's talk about first the dioxides, that the reducing nature of oxides decreases with the order SO2, SeO2 and TeO2. Rather what we find is this is a strong reducing agent, whereas TeO2 is an oxidizing agent. The reason being tellurium is not very stable in its higher oxidation states, whereas sulfur definitely will be able to get oxidized to SO3 or into the +6 oxidation state. So that's why it's a reducing agent, it's an oxidizing agent. And by nature, as I have told you, all of these are acidic, whether it's dioxide or trioxide. What is most interesting to notice that sulfur dioxide only exists in gaseous state, whereas selenium dioxide exists in gaseous as well as in solid state. When we are talking about trioxide, sulfur and selenium trioxide, they both exist in solid and in gaseous state. Halides of group 16 elements. Group 16 elements forms mainly MX6 hexahalides, MX4 tetrahalides. Along with this, they also form MX2 dihalides and M2X2 monohalides. Let us first see the oxides. Like now we know the group 16 elements, it's oxygen, sulfur, selenium and tellurium. We will not study here the oxides of halides of oxygen because they can be studied as oxides of halogens in the group 17. So we will not study it here. So we will only concentrate our studies to sulfur, selenium and tellurium. Let's talk about first MX6. MX6 hexahalides are only possible for in case of fluorides. The chlorides, bromides and iodides are not so strong oxidizing agents. They cannot oxidize these elements to their +6 oxidation state. So we have hexahalides in the form of only fluorides as SF6, SEF6 and TEF6. Of course, this will not be very stable because tellurium is not existing in the not stable in the +6 oxidation state. Now, whatever we have MX6, all of these three, they are in sp3d2 hybridization with octahedral structure. It's like this. It's fluorine, 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 fluorine and fluorine, and it's almost just like this. So this is what is the basic structure of SF6. Now these 6 fluorine forms such a stable electronic cloud around the central sulfur that makes this SF6 very, very stable. As a result, what we find is this becomes a very stable inert gas. Remember, all of these are gaseous in nature. So they becomes very stable in nature, and that is why what we find is that due to its inert, stable nature, this gaseous SF6 is used as a gas insulator in high voltage transformers. Now let us discuss MX4. MX4 with this formula, we have, yes, sulfur tetrafluoride, sulfur tetrachloride, selenium tetrafluoride, etc. TeF4 like this. Now all of these, what you need to understand is this SF4 is a gaseous substance, SeF4 is liquid, whereas TeF4 is solid. Now SF4 exists, all of these tetrafluorides exist in sp3 dehybridization, whose geometry is trigonal bipyramidal, but the structure in this case is seesaw. So it's like this, and there's a lone pair at the equatorial position. Now due to this lone pair bond pair repulsion, this angle of this axial fluorine to this axial fluorine gets reduced from 180 to 172 degree. That's why this shape is called seesaw shape. Now this is what is the nature of the halides of the formula MX4. Also you need to understand whether it is MX6 or MX4. I think that's the common in throughout the periodic table, that the stability of the halides, like if I'm talking about like M, let's take example of SF4, SCl4, SBr4 and Si4. What we will find is the stability of the halides decreases with the increasing atomic number of the halogen, because the MX bond strength, the strength of the halogen with and the central atom bond strength, decreases with the increase in the size of the central atom. That's why the stability decreases across this. Now, let's talk about the dihalides. Except selenium, sulfur and as well as tellurium, they also forms dihalides. Like sulfur forms sulfur dichloride, sulfur dibromide, remember, and tellurium dichloride, tellurium dibromide. Now what is most important to note is that these dihalides are sp3 hybridized. They are isostructural to water molecule, and their structure basically is bent shape. It's like sulfur with two chlorines here and the two lone pairs like this. So it's very much isostructural to your normal water molecule. Now what you need to again understand in this case that we cannot get fluorides, difluorides, because always any element with fluorine shows its highest oxidation state. So this is how they exist in the form of dihalides. Now let us talk about these monohalides. Sulfur and selenium, they also forms this M2X2 monohalides. Remember, these monohalides cannot exist in the as a single unit, so they exist in the form of a dimer. Like I can give you the example that this is called sulfur monochloride. The reason is there is one bond has to be between the two sulfur and one with each of the chlorine. So it's almost just like this, with both three sulfurs sp3 hybridized. So it's sulfur monochloride. Now these monochlorides are not stable. Let me talk about the selenium monochloride. When heated, it immediately changes to SeCl4 plus Se. So shows disproportionate reaction and gets oxidized to +4 and reduced to 0. So these are the natures of the halides of group 16 elements.